So, okay. So good morning and let's start today's discussion on the same topic, that is the bending stress, right? So we are deriving the relationship for bending stress, this bending stress equation. And for that we have seen few of the assumptions, and depending on those assumptions there is a when a section of a beam bends under a pure bending condition. So what is pure bending? Again I repeat, the pure bending means there is no existence of shear and the bending moment remains constant. That is what is pure bending. Okay. So when there is a bending moment remaining constant, then there cannot be shear. So basically pure bending condition, under the pure bending condition, with some assumptions, we are saying that because of the bending moment, the bending is happening in shape of an arc, right? Circular arc. And with that circular arc and from the geometry, we have derived the stress equation for bending stress, that is sigma x equal to E by rho into y, where 1 by rho is the curvature of the arc. Correct? Now, next part, let's see how does this sigma x is related to this moment m. How does this sigma x is related to this moment m? In the next part, we will try to find out that. So you see, we have seen that it is obeying Hooke's law, and sigma x is E by rho into y. So E by rho, if we see that is the constant part and y is the varying part. So because of that, we have seen that bending stress is varying linearly from top to the neutral axis position and from the bottom to the linear axis, neutral axis position. That's why we are getting some kind of triangular stress distribution like this. Yes, in the previous class we have discussed. And after that, you see, if we want to find out the moment, and if we want to establish the relationship of moment, then let's see how we can establish it. First thing, you see, what we have done here, so there is a cross section of the beam. If I cut the beam, so there is a cross section of the beam. So it may be rectangular, it may be trapezoidal, it may be of any uneven shape also. So let's say the shape of the cross section is something like this. Any shape, any kind of shape. Okay. And you have seen that this is the axis to which, at the point where the bending stress is becoming zero. Correct? Now, if I take a very small element delta A or dA over here, area, from this total area, if I take a very small element dA, and very importantly, you see, there is a notation from here to here, the distance is being shown as 1. Okay? So, y is what? Y is basically the distance from the neutral axis position to a particular point. Okay? Either at the bottom of the, either in the bottom side or in the top side. So y will be measured from the neutral axis, downward or upward, depending on the nature of stress. The values will be coming positive or negative. So if you take tensile bending stress as positive, then compressive bending stress will be negative, or vice versa. Clear? So now if I take a very small element dA, then you see how much will be the force at a particular small area getting generated. That is sigma x into dA. So this is the force getting generated, right? Stress multiplied by area is the force. So force getting generated is sigma x dA, and this sigma x dA is nothing but sigma x we have derived that E by rho into y. So E by rho into y dA. Correct? Is it clear? So now if I want to find out what is the total force in that area, what is the total force in that area, so what I should integrate it over the area. Correct? So that's what being done. So there is an integration over the area. So we are integrating over the area E by rho y dA. And if I do that, Then you see this E by rho part is constant. E by rho part is constant. So if I take E by rho out of this integral and if I do integral y dA, remember what is integral y dA over the area? It is nothing but area multiplied by yc. And what is yc? Yc is the centroidal position. Correct? So distance of the centroid. Correct? So integration y dA is what? Integration y dA. First moment of area. Y is what? Y is the distance. And moment of area. Moment of area means distance multiplied by area. That is what is moment. First moment of area is what? First moment of area is centroid. Second moment of area is moment of inertia. Right? So if I write y square dA, then it will become moment of inertia. Correct? So if you see that, so basically this term will denote somewhere to the moment of inertia. Sorry, centroid. So if now this yc is the distance from the neutral axis to the centroid, that means if I take any section like this, and if this is my neutral axis, and if this is my yc, so you try to understand what is the difference between y and yc. So y is a point somewhere, any point y. So y is varying, y is a variable, whereas yc is a fixed value, which is the distance of the neutral axis from the centroid. Distance from the neutral axis to centroid. Okay? So if I take this yc in consideration, then you can see, can area be 0? Can area be 0? A into yc becomes equal to 0. From this equation you can see, right? So can area be 0? In a beam cross section, can area be 0? Is it possible? So area cannot be 0. So which should be 0? Yc should be equal to 0. So that means it proves that if A cannot be 0, so yc should be equal to 0. What does it mean? Yc should be equal to 0 means the centroidal location is passing through the neutral axis, or the neutral axis, vice versa we should say ideally, the neutral axis is passing through the centroidal axis. So basically here the point you should understand, in pure bending theory, where we are understanding about bending stress, in such case your neutral axis, position of the neutral axis will be always passing through the centroidal axis. This is the proof of it. So yc becomes 0 means what? Yc becomes 0 means the location of the neutral axis must be at the position of the centroidal axis. Clear? With that, now if we move forward, so we have taken the force. Force is sigma into d. So if I take moment, then what will be the moment? So sigma into sigma x dA, if it is the force, then what should be the moment of this force? So if there is a small element dA over here, and the distance is y, and the force is y dA. Force is sigma x into dA. In that case, if I want to take moment about the centroidal axis, then what will be the moment? Moment about the centroidal axis. And here you see moment about the centroidal axis is moment about the neutral axis. Right? So what will be the moment about the neutral axis? If force is sigma, force into y. So in other way, if I write it this way, so my moment, if you see the moment, this moment, so dm if I write, then dm, so the incremental moment will be this one, y into sigma x, isn't it? Sigma x dA is the force, y is the distance. So what is the moment? Force multiplied by distance, y into sigma x. Now if I want to find out the total moment, and what is the total moment? So let's go back to the previous slide. And you see, this is the moment what is acting in this beam. Correct? So this moment should be equated to the integral of this moment. Means total moment. So in that small area dA, the moment is dA. So over the area if I integrate, total area if I integrate, then what I will get? I will get moment M, and I will get moment A, which is the integral of integral over the area A and y dx, y sigma x d. Correct? And what is sigma x? You can do yourself. What is sigma x? Sigma x is E by rho into y. Right? Sigma x is what? E by rho into y. So if I put the value of sigma x, then E by rho, y will come and y will multiply over here. So it will be E by rho into y square d. Isn't it? Correct? So if again I take E by rho is equal to constant, so if E by rho comes constant, then I can write E by rho, if I bring it out, E by rho over here, then integral A, it will become y square d. So you observe a typical relation over here. So what is E by A? E by rho? E by rho is constant. And I am getting another one term which is equated to the moment M, which is nothing but integral of A y square dA multiplied by E by rho. And what is integral over area A y square dA? This is nothing but the moment of area. Second moment of area is moment of area. First moment of area, central. Second moment of area, which is y square dA, is nothing but second moment of area. Right? So now, if E by rho y square dA, this is equal to moment of inertia, then what will become? The equation will become E by rho into I. Have you understood? So this is a very, very important relation for bending equation. Sorry, pure bending theory. And this equation, you will in many cases see the equation like this: M by I equal to E by. From that equation I can get the M by I equal to E by. Have you understood? Now let's say, what are the different kinds of relationship we can establish to this? So you see, M is equal to E by rho into I. So if I write this equation in a different way, then what will become this one? This will become M by EI is equal to 1 by M by EI is equal to 1 by rho. What does it mean? So you see, M is the moment. What is EI? E is modulus of elasticity. I is moment of inertia. EI is a term which will term it as flexural rigidity. Right? And what does this equation show? This equation is showing you that the curvature of the beam, which is nothing but 1 by rho. So this 1 by rho part, if I take, so the moment is directly proportional to the curvature of the beam. So moment is directly proportional to the curvature of the beam, or vice versa. If I say the curvature of the beam is proportional to the bending moment, that means more the bending moment, more will be the curvature. होगा कि नहीं होगा? If I take 100 kN load, the bending will be more than if I give a 50 kN load, right? So bending will be more, right? So more load, more bending, more curvature. So bending moment is directly proportional to curvature. On the other hand, if you take, so 1 by rho, this is the curvature, it is inversely proportional to the EI. Correct or not? It is in the denominator, so it is inversely proportional. So the curvature is inversely proportional to EI of flexural rigidity. Have you understood? Okay. So that means, what does it say? What does it say? More the flexural rigidity of the beam, less will be the curvature. So that is coming from the strength and stiffness perspective, right? So more the flexural rigidity you can produce in your beam, the less amount of curvature you will get. Is it clear? Now from this equation, now these are all mathematical equation and it's very simple to understand. Step by step you will understand. Now you see, let's say we have seen that there is a relationship of sigma x. So what was sigma x? Sigma x was nothing but E by rho into y, right? Bending stress. Sigma x was E by rho into y. So what is 1 by rho? If I write 1 by rho, so what is 1 by rho? Bola? Sigma x by E y. Correct? And what was 1 by rho I have established over here? M by EI is equal to 1 by rho. That is what is the previous equation we have established for the bending. So 1 by rho here, 1 by rho here. So I can equate this to this. So that means I can write somewhat like this: M by EI is equal to sigma x by E into y. Correct? Is there any problem in this equation? Is it okay? So now E and E cancels out. E and E cancels out. So now from this you can get equation where I can write that sigma x, or I write again one step, M by I equal to sigma x by y, or I can write sigma x equal to M into y by I. Is it clear? Sigma x equal to M into y by I. Have you understood? So this is what is bending stress. Right? So you get equation like M by I equal to sigma by y equal to E by rho. Correct? So this kind of equation you will be repeatedly getting into your bending stress theory. And all these equations are important. Anytime you may have to use any one of them for formulating or solving the problem. Clear? So now from this M by sigma x equal to M y by I. From this we will try to understand few more other things. How the sectional property will drive the bending stresses. So sectional property means beams may be of different sections. It may be rectangular beam, it may be circular beam, it may be trapezoidal beam, it may be a section of I, it may be a T section, right? So various kinds of sections you can do. So how the bending stress will vary because of that, and what will be the implication of the different sections. Okay? So that we try to understand using few more simple mathematical relations and equations, and few more other terms also we will try to understand from there. Okay? So let's say I write the bending equation, that is bending stress equation, that is sigma x equal to M by My by I, isn't it? Correct? Now you see, if I go back to my previous slide, so you see in this area, if this is the centroidal axis, and centroidal axis is nothing but which axis? Your neutral axis. So from the neutral axis position, if the bottommost fiber, this is the bottommost fiber of the section, or bottom portion of the fiber, bottom portion of the section. So if the distance from the neutral axis to the bottommost portion is C1, and from the neutral axis to the topmost portion is C2. You understand? Some books you will get this notation is given as Y1 and Y2. This is being taken from book of Timoshev's book uses this notation. Okay. C1, C2. You can use Y1, Y2. Doesn't matter. Okay. So if this centroidal, from this centroidal location, bottom fiber is at a distance C1, top fiber is at a distance C2. Can you tell me, if there is a bending like this, that means, what is this kind of bending? Sagging. So if sagging is happening, then top fiber will be what? Under compression, and the bottom fiber will be at tension, right? So that's what, if I write now, so the maximum stress will be coming over there. So you can see the sigma x is varying, your moment is constant. For a particular section, when you are loading the section, then your moment is constant. Your cross section of the beam is constant, and that's how your I will be constant. I is not varying. Which is varying? Y is varying, right? So if Y is varying, then you can see that your topmost fiber and the bottommost fiber will be having the maximum bending stress. And that's what you can see from this diagram also. The topmost portion will be having maximum, bottommost portion will be having maximum. And depending on the centroidal position, your topmost fiber stress and bottommost fiber stress may vary, or it may remain same. You understand? Because it's not always that C1 will become equal to C. When it will become, C1 will be becoming equal to C? When your section is symmetric. When the centroidal location is exactly passing through the middle of the section. Okay? So then your C1 is becoming C2. Otherwise C1 will not become equal to C. So your compressive stress, compressive bending stress and tensile bending stress, they may be differing at the top fiber and bottom fiber, depending on your sectional problem. Correct? So if I take a case of hobby, that's whatever you have said. So if I take a case of hobby, so this is your sagging. So if this is your M, so sagging bending moment case, then this one is at tension and this one is at compression. And if I take ulta, then what will happen? This is hop, and for hop, if I say for hugging moment, this will be under tension, this will be under compression, and this will be under ulta. This one? This one will be compression, this one will be tension. This here, is it correct? Tension, compression. So whatever it may be the way, okay, you can find out your bending stress using that bending stress equation. Now, if C1 and C2 are the distances, then what I can say for this sagging condition, bottom fiber will be under tension, top fiber will be compression. So sigma x maximum, okay, and under tension will be how much? So sigma x maximum under tension will be m by I into C1. Because you see, C1 is the distance of the bottommost fiber from the nucleus. Have you understood? What will be the compression? Maximum compressive bending sigma x maximum, if I say compression, it will be becoming equal to m by I. Clear? So this is another one very important thing you should understand. And you see, if I go to the next slide, or the slide we are discussing, so you see sigma max tension will become m into C1 by I, and sigma max compression will become m into C2 by I. Have you understood it? So how to find out the bending stresses at the extreme most fibers? Can you do it now? How to find out the extreme most fiber stresses? Can you do it now? I'll give one example and problem also today. Okay? Now, before getting to the problem, let's now try to understand what will be the case depending on the different sectional properties. Okay? So if I take a rectangular section like this, if I take a rectangular section like this, beam is of a rectangular section. So if beam is of a rectangular section, where the centroid will come? Centroid will be coming at the in between. So let's say I am having a section which is of width B and let's say which is of height h. Correct? Total height is h. So centroidal location from here to here will be h by 2 and here to here will be h by 2. And what I have said, neutral axis will be going through the centroidal location. So where the neutral axis position will be? Neutral axis position will be at h by 2 distance from top, h by 2 distance from bottom. So in that way, this section is symmetric section or unsymmetric section? Symmetric section. So if it is a symmetric section, then C1 will become equal to C2 will be becoming equal to H. Have you understood? Correct? So if C1 becomes equal to C2, if C1 becomes equal to C2, then what you can observe? This sigma x maximum tension and sigma x maximum compression will be becoming equal. आएगा कि नहीं आएगा? So that means in case of a symmetric section, if I consider my bending stresses at the top fiber and the bottom fiber will remain same. However, if the sections are not symmetric, then my bending stresses at top fiber and bottom fiber will be varied and changed. Okay? Now from this, if I get another one, a beautiful numerical assumption basically, and we'll term it as something. Let's say, now let's say, if I sigma x equal to m by I, my by I. Now if I write sigma x equal to m by I by y, can I write this? M by I by y. Can I write this or not? Simple. Mathematical equation, nothing else. So what I have done? I have brought I from numerator to the denominator. And then, if you see, I instead of this, so if I write, let's say, if I write sigma x, so I can write sigma maximum tension. So tension will be how much? Maximum. So maximum tension will be I by C1. I got previous equation only I by C1. Y का जगह में C1 से replace किया. Why? I am getting the tension at the bottom. So C1 is the distance of the bottommost fiber from the neutral. Clear? Now next one is sigma max compression. How much it will be? It will be M by I by CC. Correct? Now if I denote this I by C1 as a term called Z1, and if I draw this I by C2 as Z2, then what will be my sigma max tension? I can write it M by Z1. Can I write it? And what will be my sigma max compression? It will be M by Z. You understand? Simple mathematics. Right? So, this Z1 and Z2, which is the ratio between the moment of inertia and the distance of the bottommost fiber from the neutral axis, that is termed as section modulus. It's a very, very important term. And you must remember this. It's a very important term, section modulus. Okay? And this section modulus will be repeatedly used in many cases, and most of the very important usage of this section modulus you will be seeing when you will be entering and learning for steel structure design. Okay? section modulus will become very important, and many cases you have to use section modulus repeating. Okay? So section modulus concept is clear. What I have said, section modulus. So finally, I can say my sigma x, sigma bending stress for tension and compression, and maximum bending stress and compression can be expressed in terms of section modulus also and bending moment also. Correct? Now, considering this thing, now let's try to have another one understanding. So now you tell me what is the moment of inertia for this rectangular section. So if the centroidal axis is passing through this, so I moment of inertia will be what? Don't say B is H, so it is BH by moment of inertia will be BH by 12. Correct? Now, in this case you see C1 is equal to C2. C1 is equal to C2, which is nothing but equal to H by 2. Correct? Correct again. Now, considering this, if I write Z1, so what will be my Z1? I by C1. I by C1. So what is I? I is BH cubed by 12. And what is C1? C1 is H by 2. So this will make the thing like BH cubed by 12 into 2 by H. So 2 6 12 H BH square. So how much it will come? BH square by. Correct? Have you understood? So what is the section modulus for a rectangular section? And now, if I do it for Z2, what will be the value of Z2? Same, because C1 is equal to C2. So Z2 will also become BH square by. Correct? So now you can understand very easily that if the distance from the neutral axis to the topmost and bottommost fibers are same, in that case section modulus of that section for the uppermost portion and the lowermost portion from the neutral axis will also become same. That means what happens? Your Z1 becomes equal to if Z1 becomes equal to Z2, then what happens? If Z1 becomes equal to Z2, then you can see your sigma max tension and sigma max compression will also become equal. So that's how, in a symmetric section, your stresses, bending stress at the top fiber and the bottom fiber will become same. Clear? Now do it for circular section. So what will be the circular section modulus? So थोड़ा गलत हो गया क्या? BH क्यूब होगा कि BH स्क्वायर होगा ये? BH क्यूब by 12 कि BH स्क्वायर by 12? Is this correct? वहाँ पे गलत हो गया, मेरा क्यूब लिख दिया मैंने वहाँ. That will become square in the PPT. Okay? So that should become square. Now let's go to rectangular section. Sorry, circular section. Circular section में क्या होगा? What is the circular section's moment of inertia? See, if you do not remember moment of inertia for different sections, and if you cannot calculate moment of inertia, then you cannot solve problem of beam bending stress as well as shear stress. Repeatedly it will come into picture. Okay? So you must go through this. I repeatedly told you earlier also that engineering mechanics in the prerequisite subject, engineering mechanics, you have learnt about how to find out centroid and how to find out the moment of inertia. So you should refresh whatever you have learned. Okay, other than that, you cannot solve these kind of problems. Is it okay? So now, for circular section, what is this? Pi d to the power 4 by 64, right? This is the moment of inertia, I. Now, what will be C1, C2 in case of circular section? So, if it is a circular section, so this one will be d by 2, this one will be d by 2. So, C1 will be equal to C2, will be equal to d by 2. So, what is section modulus for circular section? So, section modulus for circular section, that also will be equal to Z1, equal to Z2, equal to I by C1 or I by C2, that is I by d by 2. So, it will become pi d to the power 4 by 64 by d by 2, which will give you 5 dq by 30. Okay? Clear? So this is what is section modulus. Now these are known values. Now if a section like this comes, trapezoidal section comes, then how to do it? So then you will have to apply your knowledge about finding out what is the position of centroid, right? Or you have to remember the value, memorize. And what is the value of the moment of inertia of this kind of section? Is it possible to remember for all types of section what is the value of moment of inertia? It is not possible. So you will have to come from the basic. Correct? So centroid finding and moment of inertia finding is very, very important for some regular sections as well as for some irregular or unsymmetric sections. Okay? Now for this trapezoidal section, if you take, then you see, for this trapezoidal section, it is this way, it is downward, it is thicker, flatter, right? So the centroidal location obviously will be little downward. Centroidal location will be little downward because the mass of the body is downward, right? So the centroidal location will be little downward. So if I take the centroidal location, let's say somewhere here. So if I take centroidal location somewhere here, in this case, will C1 will be becoming equal to C2? No. Will it or not? No. So you can see very easily that if I take this one as C1 and if I take this one as C2, then C1 will be lesser than C2, right? So obviously if C1 is lesser than C2, then Z1, what will be the value of Z1? Z is nothing but what? I by C1. Z1 is nothing but I by C1. And Z2 is what? I by C2. So if C1 is less, Z1 will be more. Sorry, C1 is less than C2, then Z1 will be more than Z2. Because इसका value छोटा है इससे. तो इससे जो टर्म डिवाइड करके जो टर्म आएगा, C2 से डिवाइड करके जो टर्म आएगा, this will be lesser than this one, or Z1 will be greater than Z2. So you see, in this kind of section, your Z1 will be greater than Z2. Z1 will be greater than Z2. What does it mean? Z1 is greater than Z2. What does it mean? It means that if you go back to the sigma max formula, so sigma max tension. So sigma max tension is what? M by Z1. Correct? And what is sigma max compression? M by Z2. M are same, right? M is not changing for tension and compression. M is the moment coming into the beam. So if M is same, then this is Z1, this is Z2. Z1 is less or Z2 is less? Z2 is less. Z2 is less, so which one will become more? Z2 is less, this will become more. So sigma max compression, will be more than what? More than sigma max tension. आएगा कि नहीं? Will it come? So that means the bending stress on the top fiber, compression comes up as a top fiber. So compression, bending stress in the compression is more than the bending stress in tension. That means that the top fiber will be under more compression than the bottom fiber. Correct? And this phenomenon can be very well utilized in case of some materials. That's why you see I have written like material like cast iron, let's say. Cast iron. There are various materials available. Even for concrete also if you can take. Concrete is very good in compression and very bad in tension. Right? Concrete is very good in compression and very good in tension. So, if I can get a section of cast iron or if I can get a section of concrete and if I can make my beam like a trapezoidal beam, I will get the full advantage of the material. Because compression is more and I can get, if I keep a trapezoidal section, my compression will be more at the upward section. And concrete is good in compression, so you can take a huge amount of compression. And it is bad in tension, so tension will be coming lesser. So you see, if you think about a pure concrete section, okay, so rectangular section will be very bad. Because in case of rectangular section, what will happen? In case of rectangular section, tension and compression will become equal, right? So bending stresses will become equal. So if you take a plain concrete section, let's say, then rectangular section will be very bad because concrete is not good in tension. Same is the case of cast iron also. So cast iron, steel, if you take the case of steel, steel is such a material which is very good in tension as well as it is very good in compression. So that's why steel में कुछ भी section use कर सकते. You can use any kind of section in case of steel. However, if you want to use a cast iron section, right? So in case of cast iron section, if you go for a rectangular section, then you will not get the full advantage of the material. And you will not get the advantage of the economical design of the section of the beam. Because economy is another one very important thing. In that case, what you have to do? Tension को compression के साथ equal करने के लिए you have to make the depth of the beam very large. If you make a rectangular section, then your depth of the beam you should become very large. So depth बढ़ा दोगे तो क्या होगा? C1 will become more, so Z1 will become more. So if Z1 becomes more, then sigma max T will become less. So in cast iron section, if you want to use a rectangular section, then you may have to increase huge amount of depth. May have to increase very good amount of depth at the bottom. However, if you use a trapezoidal section for cast iron, then you can use the full advantage of the material property. Is it clear? So with this, you can see there are various kinds of sections being used in this thing, in civil engineering design as well. What is the time? So we'll stop. So last part, I take 2-3 minutes later on, okay, and complete. Then we will go to understanding about what is the shear stress in beam. Okay, what is the formulation for shear stress in beam? So we will discuss in the next few classes shear stress in beam. We will stop.